Hey guys, welcome to this new story. Today, we set our sights on the very edge of the universe we can see and the mysteries that lie beyond it. At the boundary of the observable cosmos, light from the earliest stars and galaxies fades into darkness we cannot measure. This edge marks the farthest distances our instruments can reach, where space stretches, time slows, and what exists beyond is almost entirely unknown. Scientists have mapped countless galaxies, measured the background glow of the cosmos, and traced the expansion of space itself. Yet questions remain. What lies past the limit of our vision? Are there more galaxies, more stars, more worlds like our own? Could the laws of physics change in ways we cannot predict? In this video, we journey to the outermost reaches of the observable universe to explore these mysteries and reveal what the edge of everything we can see tells us about the universe itself. The observable universe is the part of the cosmos from which light has had time to reach the present-day Earth since the beginning of the universe. Its boundaries are defined not by any physical edge, but by the distance light has traveled in the approximately 13.8 billion years since the Big Bang. Light moves at a finite speed, and as the universe expands, more distant regions are carried away faster than the light they emit can cover the intervening distance. The limit created by this combination of light travel time and cosmic expansion forms what is known as the cosmic horizon. The radius of this horizon is roughly 46 billion light years in every direction, encompassing all matter and radiation from which information could have arrived to Earth since the universe began. This sphere forms the observable universe, a three-dimensional region defined by the reach of electromagnetic signals over time. Beyond this sphere, the universe may continue, but no light or other signal from those regions has yet reached any observer. Within this vast volume, every object emits light that carries information about its composition, temperature, motion, and distance. Galaxies are distributed across space in clusters and filaments separated by vast voids. Stars shine with light generated through nuclear reactions at their cores. Clouds of gas and dust scatter and absorb radiation, shaping the light that eventually reaches telescopes. Observing these signals allows for the reconstruction of cosmic history. The earliest light visible is not from stars, which formed hundreds of millions of years after the Big Bang, but from the cosmic microwave background, the remnant radiation from the hot, dense early universe. This radiation fills all space and provides a snapshot of the universe when it was roughly 380,000 years old, just after the time when the universe cooled enough for neutral atoms to form. Photons from this period have traveled across expanding space for more than 13 billion years, redshifted by cosmic expansion into the microwave region of the spectrum. The concept of redshift is critical to understanding the observable universe. As space expands, the wavelength of light traveling through it stretches. Light from distant galaxies thus arrives at longer, redder wavelengths than when it was emitted. By measuring this redshift, the velocity of a galaxy's recession can be determined and its distance inferred. The farther a galaxy is, the faster it appears to recede. This relationship is linear at smaller distances and becomes more complex at the largest scales due to the acceleration of cosmic expansion. Observations show that the expansion is not slowing under gravity as once thought, but instead accelerating, a phenomenon attributed to dark energy. The accelerated expansion influences the observable horizon by increasing the distance beyond which light will never reach, even given infinite time. This sets a fundamental limit on the volume of the universe that can be observed directly. While the observable universe has a definable boundary in principle, it is not a physical wall or edge. Matter and radiation continue beyond the horizon, but their light has not had sufficient time to reach a given point. The universe beyond the observable horizon could contain similar galaxies, stars, and structures, or it could follow a different distribution, but no direct measurement is currently possible. Scientists rely on statistical models and physical laws to extrapolate properties beyond observation, using the isotropy and homogeneity seen in the observable portion as a guide. These assumptions suggest that on very large scales, the universe is largely uniform, meaning the structures and matter distribution seen locally are likely representative of regions beyond the cosmic horizon. Light from distant objects is also affected by the curvature and expansion history of space. General relativity, massive objects bend the path of light, producing gravitational lensing. Over cosmic distances, the expansion itself changes the energy of photons. The combination of these effects must be accounted for when defining the boundary of what can be observed. The observable universe thus represents a volume where photons emitted since the origin of the universe have had sufficient time to reach the present day, modified by the expansion of space and gravitational effects. Regions beyond this volume exist, but their light has not yet arrived, and some regions may never become observable if expansion continues to accelerate. The cosmic microwave background provides a definitive marker of the observable universe's limits. Detected first in the mid 20th century, it exhibits a nearly uniform temperature of roughly 2.73 Kelvin. Tiny anisotropies in this radiation reveal the seeds of future structure, the variations in density that would eventually form galaxies and clusters. The uniformity of the CMB in all directions confirms the large scale isotropy of the observable universe, while the small fluctuations provide clues about the composition, density, and expansion history. By mapping these variations, scientists can define the volume of space from which the earliest light originates, effectively mapping the sphere of the observable universe. Instruments like the Planck satellite have produced high resolution measurements of this background, enabling precise determination of cosmological parameters such as the Hubble constant, matter density, and curvature. The finite speed of light, combined with cosmic expansion, results in a phenomenon where observers see distant galaxies as they existed in the past. Galaxies near the edge of the observable universe are seen as they were billions of years ago, in the early stages of formation. The apparent age of these galaxies decreases with distance. At the extreme edge, galaxies are observed in their infancy, sometimes as small clusters of stars or proto-galaxies. These observations provide a chronological window into the universe's history, allowing scientists to study formation, evolution, and distribution over time. The observable universe thus functions both at a spatial limit and a temporal record, encompassing both distance and cosmic history. Matter density and structure vary within the observable universe. Clusters of galaxies are connected by filaments of gas and dark matter, while vast voids contain relatively little mass. The arrangement of these structures results from gravitational collapse over billions of years, shaped by the initial density fluctuations seen in the cosmic microwave background. As distance increases toward the observable edge, fewer individual galaxies are visible, and they appear smaller and fainter due to their extreme distances and redshift. Advanced telescopes, including space-based observatories, allow the detection of these faint signals, expanding the effective observable volume and providing more detail about the universe at its limits. The concept of the observable universe also relates to the expansion rate over time. Early in cosmic history, the universe expanded rapidly, and regions that were once in causal contact are now separated beyond the observable horizon. The scale factor of the universe quantifies this expansion, and its changes over time determine the proper distances to objects at given redshifts. The observable limit is not fixed, but depends on the current expansion rate, the age of the universe, and the physics of light propagation. Consequently, the boundary of the observable universe changes slowly over time, allowing ever fainter and more distant signals to become detectable with improved instruments. Distances in the observable universe are described in multiple ways, including co-moving distance, proper distance, and look-back time. Comoving distance accounts for the expansion of space, providing a fixed coordinate system, while proper distance measures the instantaneous separation at a given cosmic time. Look back time corresponds to the elapsed time since the light left its source. Each measure offers a different perspective on the same underlying volume and allows cosmologists to translate observational data into meaningful spatial and temporal context. These metrics are essential for defining the edge of what can be observed and for understanding the universe's large scale structure. The total number of galaxies within the observable universe is estimated to be in the hundreds of billions, each with hundreds of billions of stars. The light from the most distant of these galaxies contributes to the observable limit, marking the furthest points from which information can arrive. The apparent uniformity of galaxy distribution at large scales supports the cosmological principle, which posits that the universe is homogeneous and isotropic on the largest scales. This principle underpins the assumption that matter beyond the observable horizon follows a similar distribution, though no direct evidence exists. Observations thus provide a representative sample of cosmic structure, but the total universe may extend far beyond, potentially without limit. The observable universe, in summary, is a sphere centered on any point of observation, defined strictly by the distance light has traveled since the beginning of cosmic expansion. It encompasses all galaxies, matter, radiation, and signals detectable from the early universe, including the cosmic microwave background. The edge of the sphere does not correspond to a physical boundary, but to a horizon set by the limits of light travel and expansion. Beyond this boundary, the universe continues, but no direct observations are possible. The observable universe thus provides both a map of what can be seen and a framework for understanding the structure, distribution, and history of all that lies within its reach. Space is not static. From the earliest moments after the Big Bang, the universe has been expanding, carrying matter, radiation, and galaxies along with it. This expansion occurs everywhere at once, stretching the distances between objects rather than moving them through pre-existing space. The rate at which this stretching occurs is not uniform when measured in absolute terms, but is proportional to the separation between points. In the 21st century, this relationship was formalized through observations and is known as Hubble's law. It states that the velocity at which a galaxy recedes from an observer is proportional to its distance. Distant galaxies move away faster than those nearby, and the proportionality constant, the Hubble parameter, provides a measure of the expansion rate. The Hubble constant, measured in kilometers per second per megaparsec, allows scientists to convert observed velocities into distances and vice versa, forming a fundamental tool in cosmology. Recession of galaxies is a direct consequence of space expanding. As space stretches, photons traveling through it also stretch, increasing in wavelength. This change is called redshift. The more distant a galaxy, the more its light has shifted toward the red end of the spectrum by the time it reaches an observer. Measuring this redshift provides a reliable estimate of distance when combined with the expansion rate. Redshift also encodes information about the universe's history, revealing how quickly space has grown over billions of years. Very distant galaxies, observed as they were near the beginning of cosmic time, show extreme redshift, sometimes shifting light into infrared or even microwave ranges. This effect defines practical observational limits, as light from increasingly distant regions becomes fainter and harder to detect. The expansion is not a simple, constant process. Observations indicate that the universe's expansion has changed over time. In the early universe, matter and radiation dominated the energy content, producing a decelerating expansion. Gravity pulled on matter, slowing the overall growth of space. Measurements of distant supernovae and the distribution of galaxies show that roughly 5 billion years ago, the universe entered a phase of accelerated expansion. The cause of this acceleration is a mysterious component of energy called dark energy, which permeates space uniformly and counteracts gravitational attraction on the largest scales. Dark energy's effect increases as the universe grows, pushing distant galaxies away at ever faster rates. Regions of space separated by vast distances may recede faster than light relative to one another, not because they move through space, but because the space itself between them expands. Cosmic expansion is observable through multiple lines of evidence. The redshift of galaxies was first systematically cataloged in the early 20th century. Edwin Hubble and other astronomers measured velocities of nearby galaxies and found a clear relationship. The further a galaxy, the faster it appears to recede. This observation confirmed predictions from relativistic cosmology, linking the observed redshift directly to the stretching of space over time. Subsequent surveys of distant galaxies extended the relationships to far greater distances, allowing scientists to chart the growth of the universe from its early phases to the present. Redshift data, combined with measurements of the cosmic microwave background, supernova distances, and baryon acoustic oscillations, provide a consistent picture of a universe that is expanding and accelerating. Hubble's law is not a law in the strict physical sense, but an empirical relationship. Its simplicity belies the complexity of the underlying dynamics, which involve the interplay of matter, radiation, dark energy, and curvature of space. The proportionality between distance and recession velocity assumes a homogeneous and isotropic universe where no location or direction is preferred. On smaller scales, such as within galaxy clusters, local gravity dominates, and galaxies may move toward each other despite overall expansion. On larger scales, however, the linear relationship becomes apparent. Mapping galaxies at different distances reveals the large-scale structure of space and confirms that the expansion operates at every point, influencing all cosmic structures. Redshift also sets practical observational limits. Beyond a certain distance, galaxies recede so rapidly that the light they emit will never reach a given observer, even if the universe continues to exist indefinitely. This limit defines a future horizon, distinct from the current observable horizon, determined by the ongoing acceleration due to dark energy. Light emitted now from galaxies at extreme distances may become forever unobservable. Current observations can probe only as far as light has already traveled, leaving a vast volume beyond detection. This volume may contain countless galaxies and other structures, but its contents are constrained by the same physical principles that govern expansion rather than direct observation. Accelerating expansion affects the apparent size and brightness of distant objects. As space grows, photons from faraway sources are spread over greater distances, reducing intensity. Light reaching observers is stretched in wavelength, decreasing its energy. These factors combine to make the most distant galaxies faint and difficult to detect. Space telescopes designed for infrared and microwave detection extend the reach of observations, but practical limits remain. Observational techniques must account for redshift, cosmic expansion, and absorption by interstellar and intergalactic matter. The expansion thus shapes not only the structure of the universe, but also the ability to measure and understand it. Measurements of the Hubble parameter have refined our understanding of expansion over time. Local measurements, based on Cepheid variables and nearby supernovae, produce a slightly different value from measurements using the cosmic microwave background. This discrepancy, known as the Hubble tension, has prompted ongoing study. It may indicate unknown physics or measurement uncertainties. Regardless, the core understanding remains. The universe is expanding, and the rate of expansion governs the relationship between distance, velocity, and observable limits. The expansion defines the scale of the observable universe, determines the redshift of distant objects, and sets constraints on what regions may ever be reached by light. Cosmic expansion is uniform in principle but exhibits variations in observed velocity due to gravitational interactions and local density variations. Galaxies within clusters move under mutual gravity, producing peculiar velocities superimposed on the overall expansion. Voids and filaments shape the distribution of galaxies, but on scales of hundreds of millions of light years, the linear relationship of Hubble's law dominates. This consistency allows astronomers to measure distances and map the universe on the largest scales. As surveys extend deeper into space, they reveal the web of structure that has formed within the expanding framework, showing the influence of both initial conditions and ongoing growth. Expansion also affects the interpretation of the cosmic timeline. Light from distant galaxies reveals not only spatial separation, but also temporal separation. Observing galaxies billions of light years away means seeing them as they existed billions of years ago. Combined with redshift measurements, scientists can reconstruct the sequence of cosmic events, from the early formation of stars and galaxies to the present large scale structures. The expansion history encoded in these observations provides insight into the dynamics of dark energy, matter distribution, and the ultimate fate of the universe. It defines both what can be observed and what can be inferred about the vast regions beyond current detection. The concept of space stretching under expansion also leads to counterintuitive effects. Distant galaxies can recede at apparent speeds exceeding the speed of light, not violating relativity, because the speed limit applies only to motion through space, not the expansion of space itself. This principle means the observable universe is bounded not by a true edge, but by a limit where recession velocity surpasses the ability of light to traverse the expanding distance. Light emitted from regions beyond this dynamic boundary may never reach a present observer. The interplay of expansion, light travel, and dark energy sets the framework for understanding the structure and evolution of the universe on the largest scales. Observations of supernovae and galaxy clusters confirm that expansion is accelerating. Type 1a supernovae, used as standard candles, provide precise measurements of distance over time. Their apparent brightness compared to expected luminosity reveals how expansion has changed during cosmic history. Distant clusters, measured in combination with redshift surveys, show consistent results. The acceleration implies that the universe will continue to grow at an increasing rate, carrying galaxies away from one another faster over time. This trend shapes both the observable universe today and the regions that will become observable in the far future. Expansion is thus a dynamic, ongoing process central to the definition of what can be known about the cosmos. Galaxies at the edge of the observable universe appear as faint points of light, often stretched into long red shapes due to the expansion of space. Observations using space-based and ground-based telescopes have detected galaxies whose light began its journey over 13 billion years ago. These objects formed during the first few 100 million years after the Big Bang, in a time when the universe was still young and dense. At such distances, galaxies are small, irregular in shape, and contain fewer stars than typical galaxies seen in the nearby universe. Their light is extremely dim and often shifted into the infrared, requiring sensitive instruments to detect and measure their properties. Surveys using instruments like the Hubble Space Telescope's deep field campaigns have revealed thousands of these early galaxies, mapping their distribution across small patches of the sky and providing a glimpse into the formative stages of cosmic structure. The first galaxies emerged from clouds of gas collapsing under gravity. These clouds consisted primarily of hydrogen and helium, with trace amounts of light elements formed during nucleosynthesis in the early universe. Density fluctuations in the primordial matter provided the seeds for gravitational collapse, concentrating gas in certain regions while leaving others relatively empty. Star formation ignited in these dense pockets, producing the first generations of stars, known as population 3 stars. These stars were massive, short lived, and played a key role in producing heavier elements through nuclear fusion. The remnants of these early stars enriched the surrounding gas, enabling subsequent generations of stars to form with a greater variety of chemical composition. Observing galaxies at extreme distances allows scientists to study the outcomes of these early processes, revealing how matter first coalesced into luminous structures. Galaxies near the observable edge are often smaller and less evolved than those in the nearby universe. They display irregular shapes and clumpy structures, reflecting the early stages of assembly. The rate of star formation in these galaxies is generally high as gas collapses rapidly into stellar cores. These bursts of star formation produce bright ultraviolet light, which is subsequently redshifted into the infrared by cosmic expansion. By measuring the intensity and spectrum of this light, astronomers estimate the star formation rates and infer the mass of stars within each galaxy. These measurements indicate that early galaxies were efficient at converting gas into stars, yet they remained small compared to modern spiral or elliptical galaxies. The accumulation of stars and gas over hundreds of millions of years eventually produced the larger, more organized galaxies observed in the closer universe. Galaxy clustering is apparent even at these early times. Observations show that galaxies tend to form in groups and filaments, separated by regions with few galaxies. These structures trace the underlying distribution of dark matter, which acts as a gravitational scaffold. Dark matter halos provide the gravitational potential wells in which gas collects, initiating star formation and galaxy assembly. Clusters of early galaxies highlight the hierarchical nature of cosmic structure, with smaller galaxies merging to form larger ones over time. Mapping these distant clusters gives insight into how the large scale cosmic web developed, showing that the universe's structure was already beginning to emerge just a few 100 million years after the Big Bang. These findings confirm that gravitational processes and dark matter distributions governed the formation of cosmic structure from the very start. Observing galaxies at the limits of detectability presents significant challenges. The immense distance and redshift reduce the apparent brightness of these objects, making them difficult to distinguish from background noise. Telescopes must operate at wavelengths corresponding to the redshifted light, often in the infrared range. Ground-based observations are limited by the atmosphere, which absorbs and distorts these wavelengths. Space-based instruments circumvent this limitation, providing clearer access to faint signals. Even with advanced technology, only a fraction of the earliest galaxies are visible, and each detection requires careful calibration and data processing. The faintest galaxies, potentially more numerous than those observed, remain beyond current detection capabilities, leaving the earliest universe partially hidden from direct observation, where redshift affects the apparent size and color of distant galaxies. Light that originated in the ultraviolet or visible spectrum is stretched into infrared as it travels through expanding space. This stretching reduces photon energy, requiring detectors sensitive to longer wavelengths. As a result, observations must rely on specialized sensors and filters to capture meaningful data. The observed morphology of galaxies is also influenced by the limited resolution at such distances, causing individual star-forming regions to appear blended together. Careful analysis allows astronomers to reconstruct the physical properties of these distant galaxies, including their mass, luminosity, and star formation rate. Despite the observational hurdles, each measurement contributes to understanding the universe's earliest epochs and the formation of structure at large scales. The population of galaxies at the observable edge offers information about cosmic evolution. Comparing their properties to those of closer galaxies shows a clear trend of growth and maturation over billions of years. Galaxies accumulate mass through gas accretion and mergers, gradually forming more organized structures. Star formation continues, But as gas is consumed or expelled by stellar winds and supernovae, rates decline. Over time, these processes produce the large spirals, ellipticals, and lenticular galaxies familiar in the nearby universe. Observations of early galaxies allow scientists to chart this evolution, providing a timeline for the growth of matter from the first luminous objects to the complex cosmic web present today. Interpreting observations requires models of galaxy formation and evolution. Simulations of cosmic structure track the collapse of gas into dark matter halos, the ignition of star formation, and the assembly of galaxies through mergers. These models, constrained by observations, help explain the distribution and characteristics of galaxies at extreme distances. Differences between observed galaxies and model predictions guide refinements in understanding processes such as feedback from stars, supernovae, and black hole growth. The alignment between observations and theoretical models strengthens confidence that galaxies at the edge of observability follow the same fundamental physical laws as those nearby, even though conditions in the early universe were distinct in density, temperature, and chemical composition. Surveys of distant galaxies employ deep field techniques, focusing on small regions of the sky for extended periods. This approach allows the detection of extremely faint objects by accumulating light over time. The resulting images reveal thousands of galaxies in a single field, many of which lie near the observational limit. By analyzing the spectra of these galaxies, astronomers determine redshift, chemical composition, and star formation activity. These measurements illustrate the diversity of early galaxies, from tiny irregular clumps to larger, more luminous systems beginning to form central bulges. The patterns observed in these surveys provide insight into the distribution of matter, the efficiency of star formation, and the dynamics of early galaxy assembly. Observations of early galaxies also inform the study of rionization, the epoch when the universe's neutral hydrogen was ionized by the first luminous sources. The ultraviolet light from young massive stars in early galaxies contributed to this process, gradually transforming the intergalactic medium. Measuring the properties and distribution of these galaxies allows scientists to infer how quickly reionization occurred and which galaxies contributed most to it. The timing of reionization is closely linked to the formation of the first stars and galaxies, providing a benchmark for understanding the universe's transition from a simple, nearly uniform state to a structured cosmos filled with luminous objects. Data from the Hubble Space Telescope and other observatories have revealed that reionization was largely complete by roughly 1 billion years after the Big Bang, with galaxies at the edge of observability driving much of this transformation. Distance, redshift, and cosmic time are interconnected in observations of early galaxies. Light from galaxies at redshifts greater than 6 has traveled over 12 billion years to reach present-day detectors. These measurements place the observed galaxies within the first few hundred million years of cosmic history. The faintness and extreme redshift of these objects make precise measurement difficult, yet each detection adds to the cumulative understanding of early cosmic structure. The earliest galaxies reveal both the initial conditions of matter distribution and the processes by which small, irregular structures grew into the galaxies that dominate the universe today. These observations set the stage for studying even more distant regions, pushing the limits of what is observable and illuminating the formation of structure near the edge of the known cosmos. Star formation rates in early galaxies are estimated through multiple observational methods. Ultraviolet light, corrected for absorption by interstellar dust, provides a measure of the number of massive young stars. Infrared emissions from dust heated by star formation offer complementary data. These combined observations indicate that early galaxies converted gas into stars at rates much higher than typically observed in the nearby universe. High star formation rates contributed to rapid chemical enrichment, producing heavier elements that would seed future generations of stars and planets. The efficiency of these processes underscores the rapid pace of evolution in the earliest galaxies, even while their small size and low mass distinguish them from later, more developed systems. Finally, the edge of observability itself imposes limits on what can be detected. As distance increases, galaxies become fainter, redshifted, and eventually too small to resolve. Each observation approaches a practical boundary where only the brightest or most massive early galaxies can be studied. Instruments continue to improve, expanding this boundary, but a significant portion of the earliest structures remains hidden. The faintest galaxies may outnumber the detectable ones, meaning the first billion years of cosmic history are only partially revealed. Nonetheless, surveys and detailed study of galaxies at extreme distances provide a direct window into the universe's first structures, the mechanisms of early star formation, and the development of cosmic architecture. Observations at this frontier define the outer limits of what is known and prepare the groundwork for future discovery in regions approaching the observable horizon. The cosmic microwave background is the oldest light detectable in the universe. It originates from a time roughly 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this time, photons were scattered continuously by free electrons, making space opaque. The formation of neutral atoms allowed photons to travel freely for the first time, creating a background of radiation that fills all space. This radiation has been traveling for over 13 billion years, stretched into microwave wavelengths by the expansion of the universe. Its uniform presence provides a snapshot of the universe at this very early stage, preserving information about temperature, density, and motion from a time before stars or galaxies had formed. Mapping the cosmic microwave background requires precise measurement of tiny variations in temperature. The CMB appears nearly uniform with a temperature of approximately 2.73 Kelvin, but minute fluctuations on the order of 1 part in 100,000 reveal differences in the density of matter. These variations correspond to regions slightly hotter or cooler than average, indicating areas with more or less matter. Denser regions would eventually collapse under gravity to form the first stars and galaxies. Cooler, less dense regions became cosmic voids. By studying the CMB, scientists trace the initial distribution of matter, offering a window into the universe's primordial structure and the processes that led to the formation of all large-scale cosmic features observed today. The patterns in the CMB are influenced by acoustic oscillations in the early plasma. Pressure waves traveled through the hot, dense medium, creating regions of compression and rarefaction. These oscillations left an imprint on the distribution of photons, visible today as temperature anisotropies across the sky. The scale and amplitude of these fluctuations encode information about the total matter density, the fraction of ordinary matter versus dark matter, and the curvature of space. By analyzing the angular size of peaks in the CMB power spectrum, cosmologists can infer the geometry of the universe. Observations from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have produced high-resolution maps, allowing precise measurement of these fundamental parameters. The CMB also defines the observable boundary. Photons from the surface of last scattering, the time when neutral atoms formed, mark the farthest distance from which light can reach the present day. This surface is not a physical shell, but a temporal horizon. The limit is set by when photons decoupled from matter. Beyond this surface, the universe existed, but photons from earlier epochs were trapped by dense plasma and could not travel freely. The observable universe is therefore bounded by the maximum distance that these ancient photons have traveled. While matter continues beyond this limit, no light from these regions has yet arrived, making the CMB a natural marker of the observable boundary. Temperature anisotropies in the CMB are mapped in detail using full sky surveys. These maps reveal subtle differences in brightness and polarization, providing a three-dimensional understanding of early cosmic conditions. Polarization arises from the scattering of photons off electrons at the time of decoupling, encoding additional information about velocity fields and gravitational potentials. By measuring both temperature and polarization, scientists can reconstruct the density fluctuations that seeded galaxies, clusters, and large-scale structures. These measurements also help refine models of cosmic inflation, the rapid expansion thought to have occurred moments after the Big Bang, which produced the nearly uniform, yet slightly perturbed conditions seen in the CMB. The scale of observed fluctuations informs the total energy content of the universe. Regions with higher photon density correspond to higher baryon density, while the presence of dark matter affects the growth of perturbations. Small variations in the CMB are amplified over time by gravitational collapse, creating the web of filaments and voids that define large-scale structure. Analysis of these patterns provides precise measurements of key cosmological parameters, including the Hubble constant, the density of dark matter, and the cosmological constant associated with dark energy. The CMB thus serves as both a relic from the past and a tool for understanding the universe's evolution, connecting the early universe with structures visible today. The CMB's uniformity across the sky supports the cosmological principle. Observations in every direction show similar temperature with only tiny variations, implying that the universe was highly homogeneous at the time of decoupling. This uniformity suggests that, on the largest scales, the laws of physics operated evenly throughout space. Small anisotropies, however, are critical for structure formation. They indicate regions where matter could begin to cluster, forming stars, galaxies, and larger structures. The study of these anisotropies bridges early universe physics with the later development of cosmic architecture, demonstrating the direct link between initial conditions and the universe observed billions of years later. Observations of the CMB also provide insight into cosmic inflation. The nearly uniform temperature across regions of space that would otherwise be causally disconnected suggests a rapid, exponential expansion in the universe's earliest fractions of a second. Inflation would stretch tiny quantum fluctuations to macroscopic scales, creating the initial density variations observed in the CMB. These fluctuations set the seeds for gravitational collapse, initiating galaxy formation and the growth of cosmic structure. The scale invariant distribution of these anisotropies, confirmed by high-precision measurements, supports the inflationary model, showing how early universe physics has left a permanent imprint on observable space. Foreground contamination from galaxies and interstellar matter presents challenges for observing the CMB. Radiation from our own galaxy and distant galaxies can interfere with the faint microwave signal. Scientists use multi-wavelength observations to subtract these foregrounds, isolating the primordial signal. This process requires careful calibration and modeling, as even small errors can distort interpretations of temperature and polarization. Despite these challenges, the resulting CMB maps achieve remarkable precision, revealing the minute fluctuations that encode fundamental information about the universe's composition, expansion, and geometry. The CMB also provides constraints on the total curvature of space. Measurements of the angular size of the first acoustic peak indicate that the universe is nearly flat on large scales. A flat geometry implies that the total energy density is very close to the critical value required to balance expansion. This observation has profound implications for cosmology, affecting predictions for the growth of structure, the behavior of dark energy, and the ultimate fate of the universe. The correspondence between theoretical predictions and observed CMB patterns confirms the role of early universe physics in establishing the properties of the observable cosmos. Variations in the CMB also contain information about neutrinos and other relativistic particles present in the early universe. Their presence influences the rate at which fluctuations grow and the damping of small scale anisotropies. By analyzing the fine structure of the CMB power spectrum, scientists can infer the number of neutrino species and place limits on their mass. These measurements provide a rare glimpse into fundamental particle physics using astronomical observation, connecting conditions billions of years ago with present day cosmology. The CMB is therefore both a window into the early universe and a laboratory for testing physical laws. The surface of last scattering is not perfectly sharp. Recombination occurred over tens of thousands of years, and photons experienced small variations in scattering before traveling freely. This finite thickness slightly blurs the features observed in the CMB, influencing measurements of small scale anisotropies. Understanding these effects is essential for accurate interpretation. Combined with careful statistical analysis, scientists can extract precise information about density fluctuations, gravitational potentials, and the composition of matter. These insights shape the understanding of how the early universe transitioned from a hot, dense plasma into the structured cosmos observed today. Finally, the CMB sets the ultimate practical horizon for observation. Photons from this early period define the maximum distance from which information can currently arrive. Beyond this surface, space may contain galaxies, stars, and other structures, but light from these regions has not yet reached a present-day observer. The CMB is thus both a relic and a boundary, marking the earliest epoch visible in electromagnetic radiation. It provides a reference for all subsequent observations, anchoring the scale, age, and structure of the observable universe. Through detailed study of temperature, polarization, and anisotropy, the cosmic microwave background continues to inform the understanding of the universe's earliest moments and the formation of the observable cosmos. Cosmic inflation is a theory describing a brief period of extremely rapid expansion in the universe's earliest moments. This expansion occurred within a fraction of a second after the Big Bang, far faster than the speed at which light could travel through space. During this epoch, the universe grew exponentially, increasing in size by many orders of magnitude in an almost instant. Inflation helps explain several key observations about the universe, including its uniformity across vast distances, the near flatness of space, and the lack of large-scale irregularities. By stretching space so dramatically, inflation set the stage for the formation of cosmic structure, determining the distribution of matter and energy that would later develop into galaxies, clusters, and filaments. The process of inflation involved a field known as the inflaton, which dominated the energy content of the universe during this period. The inflaton field had a high potential energy, creating a repulsive effect that caused space itself to expand rapidly. As the field slowly decayed, its energy converted into particles and radiation, filling the universe with the matter and light that would form the early plasma. This transition from inflation to the radiation-dominated phase marks a fundamental shift, establishing the initial conditions for the subsequent growth of structure. Quantum fluctuations in the inflaton field produce tiny variations in density, which were stretched to cosmic scales by the expansion. These fluctuations became the seeds for all large-scale structures observed today. Inflation predicts that regions of space, once in close contact, were carried far apart, beyond what is now observable. Areas that were initially smaller than a proton could be separated by distances larger than the observable universe. This explains why the cosmic microwave background appears uniform across the sky, even in regions that could not have exchanged information through light travel in a conventional sense. The exponential growth smoothed out irregularities, leaving only small fluctuations that would later grow under gravity. These tiny differences in density provide the basis for galaxy formation, cluster development, and the cosmic web. Observing the patterns in the CMB confirms that such fluctuations exist and match the statistical predictions of inflationary models. The rapid expansion during inflation also addresses the flatness problem. Without inflation, any small deviation from flat geometry in the early universe would grow over time, leading to a universe that is either highly curved or collapsing. Inflation stretches space to such a degree that curvature becomes negligible, producing a universe that appears nearly flat on observable scales. Measurements of the cosmic microwave background confirm this flatness, supporting the concept that inflation shaped the geometry of space. Although the observable universe is limited, the inflationary model implies that regions beyond observation would also be largely flat, maintaining the same fundamental physical laws and conditions as those within sight. Inflation produces predictions about the distribution of matter in regions that remain unobservable. Tiny quantum fluctuations, stretched across enormous distances, lead to small variations in density beyond the current cosmic horizon. These variations are expected to follow the same statistical patterns as those seen in the observable universe. Although direct observation is impossible, the theory implies that structures beyond the horizon exist and may resemble the large scale cosmic web. Some areas may contain galaxy clusters, filaments, and voids arranged according to the initial density fluctuations, while others may remain largely empty. The uniformity and structure inferred from inflation provide a framework for understanding what lies beyond the reach of light. The inflationary epoch also explains the horizon problem. Observations show that regions of space separated by vast distances have nearly identical temperature and composition, despite being too far apart to have exchanged information at the speed of light since the Big Bang. Inflation resolves this by positing that these regions were once close together before being rapidly separated. The stretching of space carried them beyond each other's causal contact, while preserving the uniformity established in the initial conditions. This mechanism ensures that the observable universe appears homogeneous, while still allowing for small fluctuations that seed structure formation. Quantum fluctuations during inflation were amplified as space expanded. Tiny variations in energy density became frozen as large-scale differences in matter distribution. These differences serve as the blueprint for the formation of galaxies, so clusters, and voids. High-density regions attracted matter through gravity, eventually forming stars and galaxies, while low-density areas remained relatively empty. Inflation predicts the scale and magnitude of these fluctuations, providing a statistical framework for understanding the universe's structure both within and beyond the observable horizon. Observations of the CMB confirm the presence and size of these fluctuations, supporting the inflationary model. Inflation is thought to have ended when the inflaton field decayed, releasing energy into the universe and creating the hot plasma of the early cosmos. This transition, called reheating, filled space with photons, neutrinos, baryons, and dark matter. The uniform distribution of this energy set the stage for the formation of the first atoms, followed by stars and galaxies. Regions separated by inflation were now part of the same expanding universe, but many remained beyond observational reach. The observable universe is a small portion of the space affected by this process, and its edge is defined by the distance light has traveled since that time, rather than a physical boundary. The consequences of inflation extend to the concept of a multiverse in some theoretical models. In these models, inflation may continue in other regions, producing pocket universes that are separate from the one observable today. Each pocket would have its own initial conditions, but those within the observable universe follow the same physical laws established during the inflationary epoch. While these additional regions cannot be observed directly, the theory provides insight into how vast the universe could be beyond the horizon. The observable universe is therefore a small sample of a much larger space shaped by inflation. The scale of expansion during inflation is immense. Distances between regions increased by a factor far greater than any conventional motion could achieve. Objects originally in contact were carried to separations beyond the observable horizon. Light emitted after this period could reach observers only from regions within the newly expanded volume. The speed and scale of inflation set the limit for what could eventually become observable, creating a fundamental boundary for light based observation. This boundary is not fixed, but determined by the combination of inflation, subsequent expansion, and the time elapsed since the Big Bang. Inflation also impacts the distribution of dark matter. As quantum fluctuations created density variations, dark matter collected in regions of higher density, establishing gravitational wells that attracted ordinary matter. These wells influenced the growth of structure throughout the universe. Even in regions beyond the observable horizon, the same principles would apply, leading to similar distributions of matter and dark matter. This provides a theoretical prediction of the structure that might exist in areas never reached by light, while still remaining consistent with observations within the observable universe. The predictions of inflation are testable through multiple methods. Patterns in the CMB, the distribution of galaxies, and the relative abundance of light elements all reflect conditions influenced by inflation. Observations show that the amplitude and spectrum of fluctuations match theoretical expectations, confirming the role of rapid early expansion in shaping the universe. While direct observation of regions beyond the horizon is impossible, the observable evidence within the cosmic microwave background supports the existence of structures created by inflation at scales far larger than the current limit of visibility. Finally, inflation provides a framework for understanding the universe as a whole. The observable universe represents only a portion of space that can be reached by light, while the total universe may extend vastly beyond this horizon. The structures, density fluctuations, and uniformity observed locally are a consequence of processes that occurred during the inflationary epoch through the amplification of quantum fluctuations, the rapid stretching of space, and the subsequent evolution of matter. The universe acquired its large-scale features. Inflation connects the earliest fractions of a second to the observable cosmos, offering a coherent explanation for both the uniformity and the structure seen today. By studying the evidence left by this epoch, scientists gain insight into the regions that lie beyond the edge of observation, revealing a universe shaped by forces and events that occurred long before the formation of stars, galaxies, or any light capable of reaching present-day observers. Beyond the observable universe, space continues, though what lies there cannot be seen directly. Based on the patterns observed within the visible universe, scientists predict that similar structures exist beyond the horizon. Galaxies likely continue to form, clustered into groups and filaments, separated by regions of low density. Cosmic voids may stretch across vast distances, empty of significant matter, while dark matter continues to shape the distribution of galaxies and gas. The arrangement of matter is expected to follow the same physical laws as within the observable portion, with gravity guiding the growth of structures from initial density fluctuations. While direct observation is impossible, extrapolating from known physics allows predictions about the composition and distribution of these unseen regions. The distinction between the observable universe and the entire universe is important. The observable universe is defined by the maximum distance that light has traveled since the Big Bang. This boundary is not an edge in space, but a limit in time. Regions beyond it exist, but their light has not reached present-day observers. The entire universe may extend far beyond this horizon, possibly infinitely, containing regions that are forever inaccessible to observation. Within these regions, galaxies, stars, and other structures could exist, forming a continuous cosmic web beyond detection. The structures seen in the observable universe are a subset of a far larger whole, representing only the portion of space from which information has had time to arrive. Galaxies beyond the horizon are expected to share characteristics with those observed nearby. They may range from small, early forming objects to larger, more developed systems formed through mergers and accretion. Clusters could assemble in hierarchical patterns, creating superclusters and filaments similar to the observed cosmic web. Voids may remain large and empty, separated by sheets of galaxies. The statistical distribution of these structures would mirror that of the observable universe, maintaining a balance between dense and sparse regions. Dark energy would continue to drive accelerated expansion, moving these regions away from each other over time and further limiting the ability of their light to reach present day detectors. Models of large scale structures suggest that the universe is homogeneous and isotropic on the largest scales. Beyond the observable boundary, this principle implies that matter is distributed similarly to regions already seen. Local variations would exist, with clusters, filaments, and voids forming naturally from gravitational collapse of initial density fluctuations. The exact arrangement is unknowable without direct observation, but statistical models provide predictions for how structures are organized. These models are constrained by observations of the observable universe, including galaxy surveys, cosmic microwave background measurements, and large scale simulations of dark matter and baryonic matter evolution. Some theoretical models suggest the universe may extend indefinitely, producing structures on scales vastly beyond current observation. In these scenarios, the cosmic web would continue, with galaxies and clusters appearing at greater distances, possibly with patterns resembling those observed locally. Density fluctuations would continue to govern formation, producing areas of high and low concentration. The processes that shaped the observable universe would operate in the same manner, though specific details of individual galaxies, clusters, and voids remain unknowable. Theoretical frameworks indicate that the overall distribution of matter could be statistically similar at all scales, providing continuity beyond the observable horizon. The concept of eternal inflation provides a theoretical context for regions beyond the observable universe. In this framework, pockets of space undergo inflation independently, creating multiple causally disconnected regions. Each region could contain its own galaxies and structures, though these remain unobservable. While this idea is not based on direct measurement, it demonstrates how cosmic inflation may produce space far larger than the visible portion. These regions, sometimes referred to as pocket universes, would follow the same physical laws established during the inflationary epoch. The observable universe is therefore one part of a much larger space, potentially filled with structures that mirror in some respects what is already known. Galaxies and unobservable regions are expected to evolve similarly to those within sight. Star formation, supernovae, and chemical enrichment would continue, governed by the same physical processes. Dark matter halos would provide the gravitational framework for galaxy assembly, while cosmic expansion carries them away from each other over vast distances. The rate of expansion increases due to dark energy, implying that more distant regions recede faster, possibly exceeding the speed at which light could travel to the observer. As a result, these regions will remain permanently beyond reach. While their exact composition is unknown, theoretical predictions suggest continuity with known patterns of cosmic structure. Clusters of galaxies beyond detection would form through mergers of smaller systems, similar to processes observed locally. Filaments connecting clusters may extend over hundreds of millions of light years, forming a vast network of matter. These structures would interact through gravity, producing motions and dynamics consistent with physical laws. Gas and dust would accumulate in dense regions, forming stars and contributing to chemical enrichment. Feedback from supernovae and active galactic nuclei could regulate star formation as observed in the visible universe. Even though these regions are unreachable, modeling their evolution provides insight into the principles that govern all space. Cosmic voids beyond the observable horizon are predicted to be extensive, empty regions with very low matter density. These voids result from the initial distribution of density fluctuations and the gravitational attraction of matter toward denser regions. Their size and shape would vary, with some reaching hundreds of millions of light years across. The existence of voids contributes to the overall large scale structure, balancing dense clusters and filaments. While no direct measurements exist, simulations based on known physical laws allow estimation of their prevalence, size, and distribution in regions beyond the visible universe. While the observable universe provides detailed information about structure, the universe beyond this limit remains inferred. Predictions rely on extrapolation, assuming that the same laws of physics apply universally. Dark matter continues to dominate the gravitational landscape, guiding the growth of structure. Ordinary matter forms galaxies and stars, while radiation and cosmic expansion influence large scale distribution. The processes observed locally, including star formation, mergers, and chemical evolution, are expected to operate in distant regions as well. In this sense, the unobservable universe is a natural extension of the familiar cosmic web, though lacking direct evidence. Theoretical frameworks, including the multiverse concept, highlight the limits of observation. While the observable universe is bounded by the distance light has traveled, inflationary models suggest that space extends far beyond this horizon. Other regions may contain their own structures, potentially with variations in initial conditions or density fluctuations. These regions cannot be observed, and their existence is inferred from models rather than detected phenomena. The multiverse remains a speculative framework, useful for understanding possible extensions of cosmic structure, but distinct from empirically measured regions within the observable horizon. Finally, the structures beyond detection illustrate the distinction between what can be seen and what exists. Galaxies, clusters, filaments, and voids may continue indefinitely, forming a universe that extends far beyond the observable portion. Their presence is predicted by extrapolation of known laws, statistical models, and the observed distribution of matter locally. While the details of these regions remain unknown, the principles guiding their formation and evolution are consistent with those observed within reach. By studying the observable universe and applying physical models, scientists gain insight into the likely nature of structures beyond the horizon, revealing the vastness of cosmic space that lies hidden from direct observation. The limits of observation in the universe are determined by the finite speed of light and the expansion of space. Light travels at a constant speed, meaning that only signals emitted in the past can reach an observer today. Regions of space that are too distant have light that has not yet arrived. Even though matter exists beyond the observable horizon, photons from these regions have not had sufficient time to traverse the expanding distances. As the universe continues to expand, some areas move away faster than light can reach, making them permanently inaccessible. This defines a practical boundary, separating what can be observed from what exists, but remains forever beyond detection. The particle horizon represents the maximum distance from which light emitted since the beginning of the universe could have reached an observer. It encompasses the entire region that is potentially visible at present, including galaxies, clusters, and cosmic radiation. Beyond this horizon, light from more distant regions has not arrived, so these areas cannot be observed. The particle horizon expands gradually as more time passes, allowing light from previously unreachable regions to eventually reach observers. However, due to the accelerating expansion caused by dark energy, many regions are carried away faster than light can approach, ensuring that certain areas remain beyond observation permanently. The event horizon is distinct from the particle horizon. While the particle horizon defines the limit of what can be seen now, the event horizon marks the boundary beyond which events occurring today or in the future can never be observed, even as time progresses indefinitely. Objects crossing this horizon recede faster than light due to cosmic expansion, and their emitted light will never reach the observer. This horizon depends on the rate of expansion, which is influenced by dark energy. Regions currently near the observable edge may eventually cross the event horizon, meaning that even if light were emitted in the future, it would not be detectable. The combination of particle and event horizons defines the ultimate observable volume in the universe, limiting both present and future visibility. Observing distant objects relies on detecting light that has traveled for billions of years. Telescopes capture electromagnetic radiation across various wavelengths, including visible light, infrared, radio, and X rays. Each type of radiation provides unique information about composition, motion, and energy processes. For the most distant galaxies, redshift stretches ultraviolet and visible light into the infrared, requiring sensitive detectors that can capture long wavelengths. Even with advanced instruments, objects near the observational boundary are faint and difficult to resolve. Exposure times must be long, and multiple observations are often combined to reduce noise and increase the signal. These techniques maximize the information that can be gathered, but they cannot overcome the fundamental limit imposed by light travel and expansion. The expanding universe alters the apparent speed and separation of distant objects. As space stretches, galaxies recede, and their emitted light is shifted toward longer wavelengths. This redshift increases with distance, making distant galaxies appear fainter and cooler in the spectrum of light received. Observational methods must account for this effect to accurately measure distances, velocities, and intrinsic brightness. Spectroscopy allows determination of redshift by identifying known spectral lines that have been displaced. Photometry provides measurements of brightness across different bands, giving insight into star formation and age. Combining these methods builds a picture of distant objects, but only within the region where light has had time to travel. Cosmic expansion also creates practical limits on resolution. Even with powerful telescopes, extremely distant objects appear small and dim, often blending together in images. Angular size decreases with distance, and faint signals approach the background noise of detectors. Observational techniques use longer exposure times, stacking of images, and adaptive optics to improve clarity. Space-based instruments avoid atmospheric distortion, capturing infrared light that ground-based telescopes cannot. Despite these improvements, there is a fundamental boundary beyond which objects are too distant for their light to be detected, defining the outermost limit of practical observation. The observable universe grows slowly over time as light from increasingly distant regions reaches observers. Galaxies that were once unreachable become visible, revealing more of the cosmic structure. However, accelerated expansion ensures that many regions will remain beyond reach. Light from these areas will never arrive, creating a permanent limit. Observational surveys are therefore confined to a fraction of the total universe, though they provide comprehensive maps of matter distribution within this accessible volume. The visible portion contains galaxies, clusters, superclusters, voids, and the cosmic microwave background, but it represents only the segment that has emitted detectable light in the past 13 billion years. Techniques such as deep field imaging extend the reach of observation, revealing faint, distant galaxies near the particle horizon. By observing small patches of sky for extended periods, telescopes collect photons from objects with extreme redshift. These methods allow study of early galaxy formation, star formation rates, and large-scale structure. Gravitational lensing, where massive objects bend light from more distant sources, also magnifies otherwise unobservable regions. While these tools extend observational limits, they remain constrained by light travel time and the accelerating expansion of space. No method can access regions beyond the event horizon. Cosmic microwave background measurements illustrate the ultimate observational limit. The CMB photons mark the farthest source of electromagnetic radiation that can reach observers today. Their journey defines the edge of observable space, a surface from which light has traveled over 13 billion years. Regions beyond the CMB surface are unseen, as light emitted earlier could not escape the opaque plasma of the early universe. Observations of the CMB reveal density fluctuations and initial conditions, but provide no direct view of structures beyond this primordial surface. The CMB thus serves as both a boundary marker and a source of fundamental information about the universe's earliest state. Observational horizons evolve as the universe ages. The particle horizon gradually increases, incorporating light from previously unseen regions, while the event horizon sets a fixed limit determined by cosmic expansion. Dark energy accelerates the expansion, moving distant objects beyond reach and preventing their light from ever arriving. As a result, the observable universe expands slowly, while a portion of the total universe remains inaccessible permanently. These dynamics define the limits of measurement and shape our understanding of cosmic scale. Models and simulations extrapolate properties beyond observation, but direct measurement is confined to the regions defined by light travel and expansion. Even within the observable universe, practical boundaries exist. Faint galaxies, diffuse gas, and low energy radiation can be difficult to detect. Instrument sensitivity, atmospheric interference, and background noise limit observation. Space-based telescopes mitigate some limitations, particularly for infrared and ultraviolet wavelengths. Techniques such as spectroscopy, photometry, and gravitational lensing improve detection, yet all observations are ultimately bounded by the speed of light and the expanding distances between sources. The combination of these factors defines both what can be observed today and what will remain forever hidden, creating a finite window into an otherwise vast and possibly infinite universe. Finally, understanding the limits of observation highlights the distinction between knowledge and existence. Regions beyond the particle and event horizons may contain galaxies, clusters, and other structures, but no information from these areas can be received. Observational astronomy, cosmology, and physics rely on measurable signals, yet theoretical models allow predictions about unobservable regions. The particle horizon, event horizon, and the techniques used to study distant objects define a framework for exploring the observable universe, while also acknowledging the permanent boundaries imposed by light travel, expansion, and time. These limits clarify the nature of the universe accessible to study and the vast domains that remain unseen. Dark matter is an invisible form of matter that shapes the universe on large scales. It does not emit light, absorb light, or interact directly with ordinary matter except through gravity. Its presence is inferred from the motion of stars and galaxies, the rotation of galaxies within clusters, and the bending of light caused by gravitational lensing. Dark matter forms halos around galaxies, providing the gravitational framework necessary to hold stars and gas together. Without it, many galaxies would be unstable and could not maintain their structure. On larger scales, dark matter forms a network of filaments connecting clusters of galaxies, creating the cosmic web that defines the large-scale arrangement of matter. In regions beyond the observable universe, dark matter is expected to continue shaping the formation of structure. Even though these regions cannot be seen directly, the same gravitational principles apply. Density fluctuations in dark matter determine where galaxies will form, how clusters will assemble, and where voids will remain. Dark matter acts as a scaffold, pulling ordinary matter toward dense regions and allowing stars and galaxies to coalesce. Simulations of large-scale structure show that dark matter filaments extend beyond the current observable horizon, suggesting that the web-like arrangement of matter continues indefinitely. Dark energy, a separate component of the universe, drives accelerated expansion. While dark matter pulls matter together through gravity, dark energy pushes space apart. Observations of distant supernovae reveal that the universe's expansion is not slowing due to gravity, as once expected, but is accelerating. This acceleration increases the separation between galaxies over time, especially those far from the observer. Some regions thus move away faster than the speed of light relative to the observer, ensuring that light emitted from these areas will never reach detection. Dark energy therefore establishes a dynamic limit on observation, shaping which parts of the universe remain permanently inaccessible. The combined effects of dark matter and dark energy determine the large scale distribution of structures. Dark matter creates dense clusters and filaments, while dark energy stretches the intervening space, expanding voids and driving galaxies apart. In the observable universe, these forces are evident in the pattern of superclusters and the spacing of voids. Beyond the horizon, the same physical principles apply. Although direct observation is impossible, theoretical models indicate that dark matter continues to guide structure formation, while dark energy accelerates the expansion of space, pushing distant objects away at increasing speed. Dark matter also influences galaxy formation in subtle ways. Variations in dark matter density provide regions where gas can accumulate, cool, and form stars. These fluctuations seed the first galaxies, determining their size, distribution, and evolution. In regions beyond observation, similar processes likely occur. Dark matter concentrations guide where matter collects, while lower density areas remain relatively empty. This creates a predicted continuation of the cosmic web, extending far beyond the edge of visible space. The invisible scaffolding of dark matter ensures that the universe maintains structure, even in regions never reached by light. Dark energy's effect becomes increasingly significant at extreme scales. As the universe grows larger, the contribution of dark energy dominates over the gravitational attraction of matter. This acceleration increases the speed at which distant galaxies recede, effectively stretching the universe beyond the observable horizon. Structures that might have once been detectable are carried away before their light can arrive. Over time, this process isolates regions from one another, limiting the amount of information that can be gathered about the larger cosmos. The interplay of dark matter and dark energy therefore shapes both the content and the accessibility of distant regions. The influence of dark energy also affects the ultimate fate of observable structures. Clusters of galaxies that are gravitationally bound will remain intact despite the accelerating expansion, but more distant structures will recede beyond detection. Filaments and voids beyond the horizon continue to evolve according to the gravitational pull of dark matter, while space itself stretches due to dark energy. Over billions of years, observable galaxies may become increasingly isolated as expansion carries more regions beyond reach. This process highlights the dynamic nature of the universe on extreme scales, where both visible and invisible components determine the large-scale layout of matter. Observational evidence of dark matter comes from multiple sources. Rotation curves of galaxies show stars orbiting faster than can be explained by visible matter alone. Galaxy cluster dynamics reveal additional mass required to prevent dispersal. Gravitational lensing produces distortions in light paths consistent with unseen mass. In the context of the universe beyond observation, these principles suggest that similar structures of dark matter continue, forming gravitational wells that guide galaxies and clusters. Though unseen directly, the presence of dark matter shapes the universe on scales far larger than those that can be measured. Dark energy is measured through the redshift of distant supernovae in the cosmic microwave background. These observations show the expansion rate of the universe increasing over time. As a repulsive component, dark energy counteracts the pull of gravity on the largest scales. Its effect is strongest on the most distant objects, or where space itself expands at an accelerating rate. This acceleration defines the event horizon and sets limits on the maximum observable volume. Even if galaxies exist beyond this limit, they are effectively unreachable due to the continued expansion driven by dark energy. Simulations combining dark matter and dark energy provide insight into the universe beyond observation. Numerical models show that the cosmic web extends far past the observable horizon, with filaments, clusters, and voids forming continuously. Dark matter shapes the density variations, while dark energy stretches space between them. These simulations suggest a structure similar in statistical properties to what is observed locally, though individual details remain unknowable. The principles governing these regions are consistent with the physical laws measured within the observable universe, offering a predictive framework for understanding what may lie beyond sight. The role of dark matter and dark energy also influences predictions about the growth of large scale structures. Dense regions attract matter and continue to form galaxies and clusters, while low density areas expand, creating voids. As space stretches under dark energy, the separation between structures increases, but the gravitational binding of dense regions prevents their dispersal. In unobservable regions, the same processes would operate, producing patterns of structure similar to those mapped in the observable cosmos. The invisible components of the universe are therefore crucial for understanding both the arrangement and the accessibility of matter on the largest scales. Finally, dark matter and dark energy together define the potential structure beyond the observable edge. Dark matter dictates where galaxies and clusters form, providing a hidden scaffold across vast distances. Dark energy drives accelerated expansion, ensuring that some regions remain beyond reach. Together, they shape the universe into a web of dense structures separated by vast voids, extending far beyond what light can reveal. While direct observation is impossible, theoretical models grounded in physics provide a detailed understanding of the likely layout of matter and the limits imposed by the accelerating universe. These invisible components continue to determine the organization, dynamics, and evolution of regions that remain permanently inaccessible to detection. The shape of the universe, or its topology, refers to the overall structure of space on the largest scales. Cosmologists consider several possibilities for global geometry. A flat universe has no curvature, meaning parallel lines remain parallel indefinitely. An open universe has negative curvature, so space bends outward like a saddle, causing parallel lines to diverge over long distances. A closed universe has positive curvature, similar to the surface of a sphere, where parallel lines eventually converge. Beyond these simple forms, space could have more complex topologies, where the universe loops back on itself in multiple dimensions. These shapes determine the global arrangement of matter and influence what exists beyond the observable horizon. Curvature affects how light travels and how distances are measured. In a flat universe, the geometry of space allows straightforward measurement of angles and distances. In a positively curved universe, lines of sight eventually converge, potentially allowing light to wrap around space, creating multiple images of the same objects in different directions. In a negatively curved universe, space expands outward, stretching distances and magnifying the separation between structures. Complex topologies could produce repeating patterns or identify points where the universe connects back on itself. These properties directly affect predictions about what lies beyond the observable region, influencing the distribution and arrangement of unobservable structures. The observable universe represents only a finite portion of the total space. The curvature and topology of the entire universe affect what exists beyond the horizon. In a flat or open universe, the extension of space is likely continuous, and structures continue outward indefinitely. In a closed universe, space eventually loops back, so the distance to regions beyond observation may be finite, though unreachable due to the time it takes for light to travel. Complex topologies introduce the possibility that distant regions may overlap or connect in ways that are not evident within the observable boundary. These properties shape theoretical models of the universe beyond what can be seen. Cosmologists infer the universe's shape by studying patterns in observable data. Measurements of the cosmic microwave background provide a map of temperature fluctuations and density variations. The angles and correlations of these fluctuations offer clues about spatial curvature. If the universe is flat, the pattern matches predictions from flat geometry. If it is curved, either positively or negatively, slight deviations appear in the angular scale of features. Observations of galaxy distribution and large scale structure further constrain possible topologies. By combining these methods, scientists estimate whether space is flat, open, closed, or exhibits more exotic connections, even if regions remain unobservable. The global geometry also affects cosmic expansion. In a flat or open universe, expansion continues indefinitely, carrying distant galaxies farther away and beyond detection. In a closed universe, expansion may slow and eventually reverse, though dark energy currently dominates, preventing collapse on observable scales. Complex topologies introduce the possibility that expansion affects different regions unevenly, depending on connectivity. These factors determine the limits of light travel, the maximum observable volume, and the structure beyond current horizons. Understanding geometry is essential to predicting how the universe extends into regions never reached by light. Methods for detecting topology include searching for repeated patterns in the cosmic microwave background. If space loops back on itself, the same region may be visible in multiple directions, producing matching circles or features. Advanced statistical techniques compare temperature fluctuations and density maps to find these patterns. While no definitive evidence of looping or complex connections has been observed, constraints suggest that if such topologies exist, they occur on scales larger than the observable universe. These analyses help define the potential arrangement of matter beyond the horizon and provide a framework for modeling unobservable regions. Curvature also influences the formation of large-scale structures. In negatively curved space, the separation between clusters and filaments increases, while positively curved space concentrates structures over shorter distances. The distribution of voids and superclusters may differ slightly depending on the global geometry. Simulations, incorporating these effects, predict that beyond the observable universe, galaxies and clusters continue to follow the gravitational blueprint provided by dark matter, while curvature slightly alters spacing and connectivity. Light travel and expansion determine which regions remain inaccessible, but underlying structure follows the same principles regardless of curvature. Complex topologies can produce unexpected effects. If the universe connects back on itself in multiple directions, regions beyond the observable horizon might eventually intersect with areas already seen in some form. Multiple images of the same object could appear in different locations if light circled the universe along different paths, though this is unlikely within the observable portion due to scale. It illustrates how global geometry governs space beyond the horizon. Even if direct observation is impossible, the mathematical framework allows predictions about the layout of structures far beyond reach. Cosmological models combine data from the CMB, galaxy surveys, and gravitational lensing to constrain possible shapes. The best current measurements indicate that the universe is very close to flat, with any curvature being extremely small. This suggests that space extends far beyond the observable region, and structures beyond the horizon likely resemble those seen locally. Large-scale filaments on clusters and voids would continue in statistical patterns similar to those mapped within sight. The slight uncertainty in curvature leaves room for minor deviations, but the fundamental large-scale structure is expected to persist. Topology also informs understanding of cosmic limits. Flat or open space implies that the universe may be infinite, while closed or complex topologies suggest boundaries, loops, or repeated connections. These properties do not change the laws of physics, which remain uniform throughout space, but they influence the arrangement and distribution of matter on scales beyond observation. Models that incorporate these possibilities allow scientists to predict the extension of the cosmic web and the organization of unobservable regions, providing insight into a universe that continues far beyond the reach of light. Finally, the shape and topology of the universe are central to predictions of what exists beyond the observable horizon. Curvature, loops, and connections determine the extent, continuity, and statistical arrangement of galaxies, clusters, filaments, and voids. Observations of the cosmic microwave background, large scale structure, and gravitational effects constrain possible geometries, while models project these patterns into unobservable space. Understanding topology links the visible universe to the larger totality, offering a scientific framework to describe regions that remain permanently beyond detection. The universe's shape sets the stage for the full scale and arrangement of structures extending into the unseen. The regions beyond the observable universe remain inaccessible to direct observation, but their existence can be inferred from physical laws and cosmological models. The structures seen locally, including galaxies, clusters, filaments, and voids, suggest that similar patterns continue in unobserved regions. Gravity, guided largely by dark matter, organizes matter into predictable distributions, while dark energy drives accelerated expansion, shaping the separation and growth of structures. Although the light from these distant areas has not arrived and may never arrive, those of physics allows scientists to project the principles governing their formation, composition, and large-scale organization. Constraints set by observations within the visible universe guide predictions about unobservable space. Measurements of the cosmic microwave background reveal the distribution of matter in the early universe and provide a blueprint for density fluctuations that seeded galaxies. Observed expansion, rates, redshifts of distant galaxies, and the dynamics of clusters provide information about the influence of dark matter and dark energy. These factors combine to define a framework for understanding how the universe continues beyond the horizon, while simultaneously establishing limits on what can be measured. Physical laws are assumed to apply uniformly, so the unobservable universe follows the same patterns as those inferred from the observable portion. Statistical models allow scientists to predict large-scale properties beyond sight. In these models, filaments of galaxies and clusters extend across regions where no light has yet reached. Voids and low-density areas continue to exist, and the distribution of matter remains consistent with what is known locally. While the precise positions and characteristics of individual galaxies cannot be determined, the overall structure adheres to gravitational principles and cosmic expansion. This continuity implies that the universe is coherent on scales far larger than the observable portion, though the details of distant structures remain inaccessible. Simulations provide insight into the potential dynamics of unobservable space. Numerical models incorporate dark matter, dark energy, and baryonic matter to reproduce the formation and evolution of galaxies and clusters. These simulations predict the persistence of the cosmic web, the growth of superclusters, and the expansion of voids in regions beyond observation. Dark energy ensures that many areas will recede faster than light can travel, isolating them from detection. Yet the underlying gravitational framework provided by dark matter continues to shape structure, illustrating that even unseen regions are governed by the same physical forces that operate locally. Ongoing research focuses on refining these predictions. Observations of distant galaxies, gravitational lensing, and the cosmic microwave background improve constraints on the universe's geometry. An expansion history. As instruments become more sensitive, astronomers can detect fainter galaxies and map structure closer to the observational limit. Future telescopes, operating in infrared and radio wavelengths, will extend the range of observable light and may reveal galaxies at higher redshifts. These advances refine models of the universe beyond direct observation, even though some regions will remain forever beyond reach due to accelerated expansion. Theoretical work continues to explore the implications of cosmic inflation, dark energy, and dark matter. Models of inflation provide a framework for understanding regions beyond the horizon, suggesting that density fluctuations extend indefinitely and that large scale structure is statistically uniform. Dark energy models predict the future growth of expansion and the eventual isolation of distant structures. By combining observational data with theoretical models, scientists can map the potential arrangement of matter, the distribution of galaxies, and the dynamics of unobservable regions. These efforts demonstrate how physics informs understanding of space that cannot be seen. Constraints also arise from fundamental physics. The speed of light limits information transfer, while the accelerated expansion of space sets permanent boundaries for observation. Gravitational interactions shape matter locally, but do not convey information across regions that have receded beyond the event horizon. These constraints define a finite observational window, even as the total universe may extend indefinitely. Understanding these limits clarifies what can be known and what must remain a matter of theoretical inference, ensuring that speculation remains grounded in physical principles. Even without direct observation, scientists can make predictions about chemical composition, galaxy evolution, and structure formation beyond the horizon. The initial conditions inferred from the cosmic microwave background suggest that matter density, dark matter distribution, and radiation density in unobservable regions resemble those observed locally. Star formation processes, galaxy mergers, and cluster assembly are expected to operate in the same manner, following universal laws. While individual objects remain unknown, the overall organization and evolution of matter continue to obey known physics, providing a scientifically grounded picture of unobservable space. Large-scale continuity also emerges from statistical homogeneity and isotropy. Observations within the observable universe indicate that on scales above several hundred million light years, matter is distributed evenly and without preferred direction. Applying this principle beyond observation implies that distant regions follow similar statistical patterns. While the exact locations of clusters and voids cannot be mapped, the overall properties and distributions are predictable. This approach allows cosmologists to extend known laws and observed patterns into unmeasured space, providing insight into the structure and scale of the broader universe. Future research may refine understanding of regions beyond the horizon through indirect methods. Gravitational waves, high-energy particle studies, and improved simulations may reveal the influence of unobservable structures on the observable universe. Observations of faint distortions in the cosmic microwave background could provide subtle clues about the large-scale mass distribution far beyond current limits. Continued development of computational models will enable more precise predictions of structure, dynamics, and expansion in inaccessible regions. Each advancement extends knowledge of the universe while acknowledging the fundamental boundaries set by light travel and expansion. Ultimately, scientifically grounded speculation provides a framework for understanding the entire universe. While light from distant regions may never arrive and some areas remain permanently beyond detection, physical laws allow informed predictions about structure, distribution, and evolution. Dark matter shapes the gravitational framework, dark energy drives expansion, and baryonic matter forms galaxies within this invisible scaffold. The universe beyond observation is expected to mirror, in broad patterns, the structures seen locally, extending the cosmic web indefinitely or looping according to global topology. These insights synthesize knowledge gained from observation, theory, and simulation. Even in the absence of direct evidence, the universe beyond observation is constrained by what is measurable. Light travel time, cosmic expansion and the laws of physics, define the accessible volume and the principles governing inaccessible space. Simulations, statistical models, and theoretical frameworks project these principles outward, producing predictions about the large scale layout of matter. While specific details remain unknown, the continuity of physics ensures that unobservable regions are not chaotic or disconnected, but follow consistent laws. The universe beyond sight is a natural extension of the known cosmos. Research into the limits of observation continues to evolve. New telescopes, more precise instruments, and advanced computational methods gradually expand the observable volume, revealing structure closer to the horizon. Observational cosmology, combined with theoretical modeling, improves constraints on expansion, curvature, and large scale structure. These efforts enhance understanding of unobservable space indirectly, allowing predictions about the arrangement, evolution, and dynamics of matter beyond sight. Even as boundaries remain, science continues to build a coherent and predictive picture of the universe as a whole. Finally, the study of unobservable regions illustrates the interplay of measurement, theory, and inference. Observations define constraints, physics provides laws, and models extend knowledge into areas that cannot be directly accessed. Dark matter, dark energy, and gravitational processes shape the distribution and evolution of matter. Cosmic expansion imposes permanent limits, while statistical homogeneity allows extrapolation of structure. Through these principles, the universe beyond the observable horizon can be understood scientifically, not as speculation alone, but as a natural consequence of known physics and cosmology. Even unseen regions remain predictable in form, behavior, and organization, forming an extensive continuum that extends far beyond the light we can detect. We've reached approximately 150,000 characters. The story is complete.